the occasion to talk about that. So maybe some of you have heard of something called limits of graphs. That's a topic that started maybe 10-15 years ago. It has many facets. People talk about graphons, for example. People talk about limits of converging sequences of graph. People talk about flag algebras. And these are essentially all the same objects. And so it's an object that you can look at from a measure point of view, from an extremal combinatorics point of view, and from an algebraic point of view. And it turns out that this theory that was developed for graphs can work for many other classes of objects. Okay, and if you go and look at the paper by Razborov on flag algebra, you see that it's written in a very formal way, not just for graph, for structures that have certain properties. And so it's clear when you talk with people like Jean-Sébastien Sereni or Jan Volek, who know limits of graphs, that you could apply this to other structures, including geometric ones, like order types. So this is what we did. So this is joint work with Alfredo Hubbard, who was here for a while, and Rémi Desjoinnes-Overclos, Jean-Sébastien Sereni, and Jan Volek, who are three people specializing more on the limits of graph side. And Alfredo is, like me, more coming from the geometric side. So we didn't do anything new regarding limits of graph. What we did was check how the ideas from this theory for graph applies to geometry and what we can get from it. It's clear that it applies. The question is, does it give interesting results? Okay, so I'm going to assume that you don't know already what exists for graph. I'm going to define things from scratch, but for order types, so that you get the geometric view. And the results that you get are a bit different probably from what you would get from for graph. So first, let me recall what order type is. Unless everybody in the room knows what an order type is? No? Okay. So, if you have points in the plane, it's very natural to associate to them, if you want to think about point sets combinatorially, an orientation. That's the first information. That's one of the most basic information. So if you have P, Q, and R, you might want to define the orientation of P, Q, R as, say, a number 1, 0, or -1 that tells you whether the triangle PQR is clockwise, counterclockwise, or flat. Okay, and so -1, 0, 1 tells you whether PQR is clockwise, counterclockwise, or flat. And one way to describe this algebraically is to look at the sign of the determinant of point P, point Q, and point R. Okay? Don't ask me which of these is clockwise, which of these is counterclockwise. I always get it wrong, but you should be able to figure it out. Once you have that, you can decide that two point set, P and Q, are equivalent if and only if there is a bijection that preserves all orientations. Okay, so that's a way to think of your point set and neglect the precise coordinate, but really care only about how the points are placed with respect to each other. Okay, so there exists F from P to Q, that is bijection and orientation preserving. So two nice things about an order type is simply an equivalence class for this relation. So then two nice things. First thing is, if you fix the size, no, you only have a finite number of order types for n points. For any n, there is a finite number of order types of size n. Simply because, for instance, you could just number the points and record for every triple which is a value, and so you get at most n cubed choices. So you get at most 3 to the n choose 3. Of course, not every sign vector can be realized, so you have much fewer actually, but you have a finite number. The second interesting thing is order type encode many properties. For example, if you want to show that K5 cannot be drawn in the plane using straight edges, all you need to do is to show that for 5 points, you cannot do that. So instead of looking at all 5 tuples of points, you can look at order types, because order types of size 5, because order types will encode intersection of segments. Okay, so it turns out you only have 3 order type of size 5 that are not degenerate, so that are simple, so no 3 points on a line, and they look like this. You check that for each of them you find an intersection, and you're done. You've proven that K5 cannot be drawn in the plane. So, just for sanity check, right? So there's only one order type of size 3. I'm going to look at simple order type. Order types. Which means that no 3 points are aligned. And I'm going to look at finite. Possibly big, but finite, simple order type. So there's only one of size 3. There are 2 of size 4. And there are 3 of size 5. Those 3 here. And size 6 you have 20, so I'm not starting to draw them. So there are a number. So there is a database of order types. So if you want to have the list of all possible order type, you can go to a website. There is a database. They could map them up to size 11, maybe a bit more. But I think from size 12 you need to order the DVD or something like that. The next natural thing that you may want to do with order type, after you can, so when you have this type of combinatorial structure, the first natural thing to do is to enumerate them. When you can no longer enumerate them, the natural thing to do is to sample, to generate random ones. Okay, so that's the first question I'm interested in, is can we generate a random order type of size n? And so, in general, I'm interested in, so for the sake of fixing the question, let's say I want to generate them uniformly. So I fix a n, there's a finite number of order type of size n, and I would like to pick one uniformly at random. Okay, so is it easy? Can I do it? You may say, okay, what I can do is I can pick, say, the square, the unit square, 0, 1, 0, 1, pick n points at random here. With probability 1, I will not get 3 aligned points. So with probability 1, the order type of those n points will be a simple order type of size n. And that's my random order type. It turns out that this is far from being uniform. Okay, there's Imre Barani, for example, looked at what the probability is that your points are in convex position. Your n points are in convex position. And this is more than the average probability. Much more. Okay. A second question. So order types encode crossing of straight lines. And there's a question that people are interested in discrete geometry. It's if I try to draw the complete graph Kn in the plane, how many crossings do I need to have? And here I'm talking about straight line edges. So what is the rectilinear crossing number crossing number of Kn. So we know that there's a positive fraction of the quadruples of points that will define a crossing, and the question is, what is this minimum fraction? Okay, and this is encoded in order types, of course, because this is equivalent to asking, assume that I have a sequence of point set, that I have a point set that is arbitrarily large. What is the minimum proportion of convex quadruple I can find there? Every time you find two edges that cross, the 4 points are in convex position. That means they realize this and not this. And vice versa. Every time you get such a situation, two of the edges that you're drawing will cross. Okay, so this is the minimum number of convex quadruple so the minimum proportion in arbitrarily large So far so good? And it turns out that limits of order type, so limits of graph applied to order type can tell us something about these two questions. Okay, so at this point perhaps I should point out that so some of you may care about other combinatorial objects such as arrangement of lines, arrangement of pseudo-lines, sorted networks, oriented matroids. All of these are related to order types, okay? And for all of these, you should be able to also apply the ID from graph limits to them and maybe mechanize it, okay? But I'm not going to say more about that.
Sorry, what is a rectilinear crossing?
So I minimize over, so it's another way to put it is the infimum over a point set in the plane of size n. So assume of size n. So I assume I draw the complete graph using this as a position for the points. So I'm looking at what is the proportion of pairs of edges that cross. Okay, so number of edges of pairs of edges that cross divided by n choose 4. Oh, actually, n choose 2 squared.
And that's somehow exactly equal to the number of...
Yes. So if I should, yeah. Because if you give me 4, so if you give me 2, so given 4 points like this, I will draw those 2 edges. So I will get a crossing.
So the edges are straight lines.
Are straight line, yes. That's why we talk about rectilinear.
Okay.
There's some literature discussing crossing number versus, so rectilinear versus Jordan curve crossing number. So I don't know if the answers are the same here for that problem. Okay. Okay. So to define limits, a natural way is to first define what is the density of an order type in another order type. Okay, so take P and Q, 2 order types, and let me define P of PQ So that is the density of P in Q. It's a probability that if you take that number of points in Q uniformly at random, what you obtain is something with the same order type as P. Okay? So that is a probability that that R in Q are with the same size as P are chosen uniformly is satisfies okay. So if you take, for example, the probability the P of this in this, what you get is okay. This one is easier. It's one. Okay. This one?
4, 5.
So if I drop this point, so I'm choosing 4 points among 5, that's the same as choosing 1 point uniformly and dropping it. So if I drop the middle one, I'm in convex position. If I drop this one, I'm in convex position. If I drop this one, I'm in convex position. But these two, yeah. So that's 3/5. And here, 1/, only this one gives me 4 in convex position. Okay. Now, consider a sequence of point set where the number of points goes to infinity. So a sequence of point set that will meet this arbitrarily large requirement. So consider a sequence Pn where each Pn is in R2, simple, finite, and the size of Pn goes to infinity. It is convergent if, so for any point set, any order type P, I can look at the sequence of density of the order type of P in the order type of Pn. Okay? And if all these sequences converge, I call my sequence convergent. Is as n goes to infinity. And in that case, the limit of Pn of the sequence is a map that sends an order type to the limit of its densities. So it might be weird. You take point set, a sequence of finite point set, and the limit is a map. Well, you take a sequence of rationals, and the limit is a real. Right? That's. It turns out that this is a good object to look at. So there are a few properties that are immediate for this limit.
You did not assume Pn as endpoints.
No. Often we do that, or sometimes it will be convenient to assume that Pn, for example, has n squared points. but no. What's important is that it goes to infinity.
So limit of PL is P or its probability? It's a function. It's a map. It's a map.
So this is a map.
From order types to probabilities.
Yes. So it's a map from the space of all order types. So let's call this all order types to 0, 1. Yes. So this map, in fact, it's basically an element of 0, 1 to this, right? It's a sequence. You can write it as a sequence. This happens to be compact. So that means you can always because this is compact, you will always be able to find lots of examples. I mean, there are lots of limits of order type because roughly every graph defines you such a sequence. So if you take any sequence of graph, there will be a subsequence that will converge in that sense.
Any sequence of order types?
Any sequence of order types, there will be a subsequence that will converge in that sense. Simply because these things, if you look at the vector, it takes value into that. So you get every sequence of order type gives you a sequence of value in that space. It's compact, so there will be a converging subsequence. So just to say, it's not an empty definition. There are many examples. There exist many examples. I haven't shown you any yet. There exist many. Okay. Yes. Okay, so to do that, let me first look at certain properties of this before that. I'll come back to give you an example. Or I can give you one example that is very easy. Take Pn being the order type of n points in convex position. This function maps P to 1 if this is in convex position and 0 otherwise. That function is a limit of order type. If you ask me for a second one, no, I'm in trouble. It takes a bit more effort. Okay. So the point is this object, so as I define them, it's basically extremal geometry. Okay, you take sequence of point sets and you look at density of subset in those. If you look at this question of the regular crossing number, a different way of putting it is take any limit of order type. What is the minimum value it takes on 4 points in convex position? Okay, so a crossing question, so Q2 is equivalent to asking what is the inf over all limits L of 4 points in convex position. Same question. So there's a way to look at this from a discrete probability point of view, because if L, so limit of order type. Okay, a limit of order type means the limit of some converging sequence. Then, so for every n, L defines a probability measure, probably distribution over the order type of size n. So why is that? For any order type of size n, L of that order type has value between 0 and 1, so it's positive. And for any, so okay, let me call this K. Now, if you fix k, and you take n such that Pn is larger than k, these P of order type of size k, Pn, define a probability distribution. They have to sum to 1. Because when you take a subset of size k in P, the various order type you get will cover all the subset of size k. Okay, so for any n large enough, these things sum to 1 when you sum over P of size k. That means that in the limit they also sum to 1. So it's a probability distribution. Okay? So we can think of L as a family dk where dk is a probability distribution on, and let me write this omega k, the order type of size k. This sequence of probability distribution has some properties. So for any A and B, for any P of size A, we have the following. The probability that you get the order type of size P with the probability distribution of that parameter. Well, what could you do? You could take a larger point set, a point set of size A, of size B. So take a point set of size B and subsample. Okay, so the sum for all order type Q in omega B. So for any P in omega A. So you look at the density of P in Q, and you multiply this by dB of Q. This is simply expressing that when you're sampling A points from your large point set, A points uniformly, it's the same as sampling first B points uniformly, and then among these B points, you subsample and you get A points. Okay? So this is true. And it turns out that dA is a limit of order type. If and only if it satisfies this. Okay, so the way you do that is, the way you prove that is basically you sample a sequence of order types for larger and larger sets, and you prove that with probability 1, that sequence that you sampled is a convergent sequence whose limit is precisely this set of distributions. Okay? So if you come back to my question number 1, which is about sampling order types, what this means is the object limit of order type, it describes any method you could think of that generate random order types and which has this hereditary property. So any method of sampling order types that is hereditary should be accessible from a limit of order type. Okay? So this means the object is quite general. So it also gives me access to a very furnished family of examples, because now that means that I can take any probability measure in the plane, say uniform in a square. I just want the probability measure to have the property that if I take 3 points at random, they are, with probability 1, they are not aligned. Okay? So, let me, example. Let mu be the uniform measure in the square. Or if you prefer the disk or whatever shape, you take any uniform probability, any probability measure in the plane. Okay? And define L of P to be the probability that the right number of points, P points sampled I from mu, realize P. Okay, so L of another type is just a probability that when you sample the right number of points from mu, what you get is that order type. Well, for any mu, so L is a limit of order type. Simply because this function defines the probability distribution over the order type of a given size and satisfies this. If you want to satisfy to sample 10 points, you're free to sample 25 and throw away 15. You will get the same probability law. Okay. And this, by the way, now I started what I intended as being 3 geometric measures. So here's one question. Is there any limit of order type that cannot be realized in this way? If it could be, then that would mean, for people who have seen graphon before, that means that we have a much simpler model for limits of order types than graphon, because for graphon you have a similar measure that is defined, but then you have 2 levels of randomness that you have to apply. You first have to choose the value, n reals, so you have a function from 0, 1 times 0, 1 to 0, 1. You choose n reals, and that gives you an n by n matrix with parameters. And then you run these values, the entries of the matrix, to 0 and 1, or 1, as Bernoulli variables with those parameters. And that random matrix that you took is the incidence matrix of your random graph. Okay, so just for those people who have looked at graphon, when you look at limits of graph, you have a similar continuous object that represents your converging sequence of graph, but the relation is actually more complicated than this one. You have 2 levels of randomness you have to apply. If you look at, you can think of order types as hypergraph, 3 uniform hypergraph. For that, you have a model also of limits of hypergraph, converging sequences of hypergraph. If you look at the random model for hypergraph, it's even more complicated. Okay, so if this were true that every measure, for every limit there is a measure so that this is a limit, it would be very nice. But of course it's not. So here is an example. So define, let me define this. So I take a parameter t between 0 and 1. And I define a measure. This is a measure. So I basically take 2 circles. They are concentric. One has radius 1. The other one has radius t. And my measure is just, first you put half of the measure on each circle, and then it's uniform with respect to Lebesgue. Okay? So 1/2. 1/2 and uniform. This, so this is a measure. So I can look at at L. This is a limit of order type. Order type defined by the measure Okay, in this sense. So let me call this L mu. Now what I do is I take the sequence L of, say, this 1n. This is a sequence with values, so it's a sequence in 0, 1, n. This is compact, so there is a converging subsequence. Okay, there is a sequence. This converges. There exists a converging subsequence, and let me call this like this. And that thing is a limit. It's a function in this. Okay, it's a. You can basically show by limit that it satisfies this. So it has to be. It is a limit of order type, but there is no measure that represents it. The intuition is very clear, right? As n goes to infinity, this tiny circle gets to a point. So that means that the natural candidate to be a measure representing this would be a unit circle and a point, with half of the measure in the direct mass in the middle and half on the circle. But this charge is line. Okay, the probability that 3 points are aligned is at least 1/8, because the probability that 3 points are equal is at least 1/8. So this doesn't define a limit of order type for simple order types. The sum of the probability of the simple order type of size n will not be 1. Maybe if I have some time at the end, I can give you a sketch of how you prove that. So it's not completely obvious. So there is no measure mu such that L mu is this. So this is the bad news. Oh, actually this was a 4. There is a good news when you think about that. So let mu be measure in 2 that charges no line. So again, what I mean is, for any line, the measure on that line is 0. So the probability that 3 points are aligned is 0. Assume that the support of mu has non-empty interior. What it means is there is a point where no matter how small a disk you place centered at that point, the disk will have strictly positive measure. Okay? So then for any measure mu prime, L mu is the same as L mu prime if and only if, let me say only this so that I state it more easily, mu prime is the projective image. So if you take a measure in the plane, say uniform on a square, and you apply an affine transformation, that will not change the order types. In fact, even applying a projective measure that sends a line that does not intersect the support of your measure to infinity will not change the order type. And this tells you that it's an if and only if under these assumptions. Okay, so when you're trying to understand, when you're trying to study measures, limits are maybe not a bad way to study measure, because it's a rather faithful representation. So here we need something. We need we use that the support has non-empty integer. If you drop any assumption, then you cannot have anything like this, anything nice. One reason is if you look at the first example of limit of order type, which is the one that puts probability 1 when you're in convex position and 0 otherwise. Okay, so any measure where the support is in convex position will give you that limit. So you can think of a uniform measure on a circle. Now you can turn your circle into a Cantor dust. Still works. So that means that if you have a way to transform one measure into the other, that transformation will not preserve the dimension. Okay, so that measure has lots of different realizations that are very unrelated one to the other. But as soon as you have one point, and let me emphasize that I'm not assuming anything on mu prime here. So I only need one interior point in the support of mu, and anything else that realizes the same limit must also have non-interior support and be projectively equivalent to mu. Okay. And the algebraic viewpoint. So we have that for any order type omega in omega A, for any b larger than A, we have that, and for any limit L, we have that L of omega is a sum for omega prime in omega B of P of omega omega prime, L of omega prime. Okay, so I'm just rewriting this above. We can have a more general relation. We can define the splitting probability I'm looking now at PW, W prime, W second. So it's a probability that when you take an order type, this order type, you pick a realization, so you have a point set. Now you split this point set uniformly into a subset of this size and a subset of that size. What is the probability that you get subset that realize precisely this and that? Okay, this is a probability that splitting uniformly a realization of omega 7 into P division Q with P size omega and Q of size omega prime gives and Q. Yeah. So in particular, this is non-zero only if size of omega plus the size of omega prime is equal to the size of omega second. Okay? So you give me, I take a larger point set and I split. And I think it's a good exercise in discrete probability to show that this relation generalizes. So for any limit, we have that L of omega times L of omega prime is a sum. So for any omega omega prime other types, and k larger than k equal plus omega prime. Okay, you sum over all the other type of the right size of the probability of splitting omega second into omega and omega prime, and the density of omega second. Okay, when you do this computation for, instead of L, you use the density in a finite point set Pn, you're comparing two events. One event is pick this number of points, look at the random order type, pick that number of points, look at the random order type. This event is pick a point set whose size is the sum of these two guys and split it. They are not the same event because here those two guys that you pick at random, they could overlap. So it means the union, maybe they cannot be obtained from taking a larger point set and splitting it. But the probability that this happens goes to 0 as the size of your point set goes to infinity. So in the limit, they are the same. Okay? And it turns out that this here is equivalent to that of the guy. Okay. So now why did I bother you with that? Because it gives some idea about how you could set up a product on the space of order type, and how this product would capture what the limits are. So what you can do, you can define, so now we can define a product. Omega times omega prime. I'm going to define it as a sum for all omega second, which are order type of size, the sum of these two, omega and omega prime, of the probability that splitting omega second give me omega and omega prime, times omega second. Okay, that's a definition of a product by definition. So the product of two order types is not an order type. Okay, so weighted sum of order types. So I can extend it to a product on the weighted sums of order types just by linearity. Okay. And now I know that every time you give me a limit, the limit is compatible with this product. Okay, L of omega times omega prime will be L of omega times omega prime. So limits will correspond to homomorphism, algebra homomorphism. In fact, if I really want to work carefully, I look at something that is a bit smaller than this. I want to kill all these identities. So I want to kill all the relation of the form omega equals the sum for omega prime in this size of this. Okay? And the limits, they pass to the quotient as well. So let me take a quotient where K is the set of all omega minus the sum for omega prime in omega b of p of omega prime, where omega is in this and b is larger than omega. Okay? So this is a subset of my vector space. I quotient it out, and the theorem is that the limits are exactly the homomorphisms the algebra homomorphism from A to R that map pure order type to something positive. Okay, so in this space, some elements are of the form one order type, for which the coefficient is 1 and everything else is 0. Those are the pure order type. Okay?
What is R to the omega here?
So it's all formal sums of order type where the coefficients are in R. Okay? Now, why is this interesting? Because it allows you to generate lots of inequalities on densities. Because if you give me, say, omega 1 plus omega 2, or omega 1 minus omega 2, these are two order types. I look at their formal difference. I raise it to the square. In that sense, in the sense of that product. I will have, this will write as a sum of alpha I, omega I, okay, omega I, let me call this omega and omega prime. It will write in this form. Okay, yeah.
Can we put 0, 1 to the omega? Is that possible as well?
Can we what?
Is it possible to, instead of say R, because all the coefficients are probabilities, right?
No. Here, sorry, extend to a product on the vector. So I'm looking at the R vector space generated by omega. So I'm looking at, so think of a vector space where every order type has one dimension. And I'm looking at the R vector space on this.
Okay.
So it's not, I'm not restricting to 0, 1. Okay, so it's the same as...
You're defining a product of two order types, right?
Yes, but then I'm extending this product to 10 omega times this over 100, for example.
Okay, I see. So
This is what I mean.
oh, I see. A vector space.
The vector space, yeah.
Okay.
So the idea is, here I'm looking at order types, but what I end up with is a linear combination. So of course I could just look at, the natural object is to have some product that remains in the same space. So I have to extend to linear combination of order type. I could restrict to linear combination with weight in 0, 1, but it turns out, why limit that? Okay, so okay, so then I don't look at this R vector space, but actually at some quotient space because I want to remove certain relations, and it turns out that the limits are this. So that means that, for example, if I take this product and I expand it, I get a certain weighted sum of order types. This implies that for any limit, the sum of the alpha I L of omega I is positive. Simply because this is L of the sum of the alpha I omega I, which is L of omega 1, omega minus omega prime squared, which is L of omega minus omega prime squared. Okay? What is that good for? Okay, let's come back to the first question. The second question. The rectilinear crossing number of the complete graph. Let me call this C4. So C4 is a minimum over all limits of OTL of L of this. I claim that C4 is at least 0.2. Why is that? I can simply look at all order types of size 5. There are 3 of them. In each of these order types, I have at least one-fifth of the quadruple are in convex position. So I can just apply the formula star, which I deleted. Yeah. So, because L of this will be 1/5 of L of this plus 3/5 of L of that plus L of that. Okay? Just by the density, I'm just applying the density formula. That L of this is a sum for all order type of size 5 of the density of 4 in the order type of size 5 times L of this. Okay? And this is at least 1/5 over times L of plus L of plus L of okay, and this is 1. So that's a very trivial bond, right? Let's say it's a complicated way to say something very simple. If you want to improve the bond, you go to size 8. And what you will get, you look for the 8th tuple of points that has the smallest possible density of points of quadrupling convex position, and you will find 19/70. Okay, which is 0.2714, blah, blah, blah. Now what you could do is look at the following things. You take 6/25 minus 11/125 times this. So these are 2 point set of size 4, 2 order type of size 4. When I take the product, the square, I get a sum of weighted order type of size 8. Okay? You add the right thing, 298,819 over 93750 times the sum for all the order type of size 8. Okay. And this you find to be, well, it's a sum of A omega omega for all order type of size 8. And you check mechanically that AW is always larger than P of this in W. Okay? Well, then this means that when you take any limit, you apply it to this, you apply the first star formula, you get something that is larger than this, which is larger than that. Okay, and so you get that this is larger than this number, 298,819 over 10,93750, which is roughly 0.2732. So you improved a bit on that. How did we get these numbers? How could you possibly try to improve this? Well, you can search for the right inequality by semi-definite programming. Okay, so you can actually try to optimize the right values. You're looking for basically a vector dot product whose square will give you the right inequality. Okay? And in fact, you're searching into another way to think about it is your limit, you can think of them as functions that have to satisfy a set of quadratic inequality. They must satisfy them. So you can search in that space using semi-definite programming. Okay, so Jan Volek was actually working very hard on this. And so he set up some semi-definite program, some way to do this semi-definite program. He got to work on that. So we didn't improve the best known bound on C4. That we came short. But we got a not so bad one. So let me give you in 1 minute what we can prove. So we could prove that C4 is at least 0.378. The best is 0.3799. Okay, so I think we came 10 years too late to have the best bound. Anyway, but you just press the button, you change the question, you press the button, and you get that C5 is at least 0.06085, blah, blah, blah. And there is an example that shows that it's at most 0.0625. Not too bad. Okay, you want C6? Yeah, we could compute some lower bound. 0.018311. There's example.
C5 a number of
5 tuples in convex position.
5.
Yeah. Yes. 0.005822. Well, this is again away by a factor at most 2. What we could show also is that for any limit order type, there exist 2 order type of size 6 such that the value for one is strictly larger than 1.8 times the value for the other. Okay, so what does it mean? It means that when you look at the 6 tuple, it will be non-uniform by a ratio that we can bound from below. And this applies to any limit of order type, so to any method for generating them at random that is consistent with subsampling. So that means if you're really trying to generate order types in a way that is uniform, you really have to get away from that. Okay, it's not a surprising fact, but if you're trying to prove it, it's not so easy. Okay, and perhaps I should stop there.